All right, so hello everyone. Welcome to the afternoon session of the joint lecture series of the MSc departments between SNU and NUS. So this is the second day, and for this afternoon session, we have Professor Seung-woo Han from SNU, and he's really the best expert in first principle simulations about material science and engineering. Okay. So before starting our lecture, let me briefly introduce our lecturer. So Professor Seung-woo Han is a professor in MSc department of SNU. He majored in physics and he got his degree from bachelor through PhD in physics, but now he's a professor in our material science and engineering department. And okay. And for a few more announcements, we are going to record this video and it will be later uploaded to the YouTube channel of our department. But I still encourage you to attend the lecture as much as possible, so we can interact more with the lecturer, so you can learn more things from this live lecture. And I also like to ask you to play your camera, so I think that will help you to focus more onto this lecture. Okay, and this lecture is about 1.5 hours, but this schedule is flexible. So if the lecturer wants, you can use more time as much as you want. And students can post questions in the chat box, or you can speak up later when the lecture is done. Okay, so that's a short intro. So let's welcome our lecturer, Professor Seung-woo Han.
Okay, thank you. Thank you, Professor Zhang, for the kind introduction and also invitation to this lecture. And welcome everybody. Good afternoon. Welcome to the lecture. And this is about atomistic modeling of materials. So here in this short lecture, I will briefly touch on the main topics. The first one is classical molecular dynamics, which is the basis of any kind of atomistic modeling. And then I will jump on to the ab initio method, or quantum mechanical method. And then I will also introduce, in the last part of my talk, I will introduce the most recent development of the machine learned the technique in this atomistic modeling. Okay, so I am Seung-woo Han, and I am leading the materials and data and informatics laboratory. Okay, let's begin with this the simple picture. This is a cup of the water, and it's quite silent. But if you zoom into the surface of the water, then you can find that the sound, the music is included in this video, and so the atoms are always moving around. And at the surface, actually, the temperature is very close to boiling temperature. And so atoms sometimes with high enough kinetic energy, they will depart from the surface. And this is the evaporation of the water molecule. And also some of the water molecule from the outside, it joins and it approaches the surface, and it joined at the part of the water. And so this is very dynamic, the picture. So basically, this gives you an idea that if we can describe everything that we observe in everyday life and also in material science, they come from the atomic motion. And therefore, if we can describe the atomic motion, then maybe we can predict the properties and the process of the materials. Okay, such an idea, the most very radical and the fundamental approach, it is actually envisioned by a long time ago by the famous scientist Laplace. And here, to quote, we may regard the present state of the universe as the effect of the past and the cause of the future, an intellect which at any given moment knew all of the forces that animate nature and the visual positions of the beings that compose it. If this intellect were vast enough to submit the data to analysis, could condense into a single formula the movement of the greatest bodies of the universe and that of the lightest atom, for such an intellect, nothing could be uncertain, and the future, just like the past, would be present before its eyes. Actually, this is such an intellect that, with a huge, capability of the computation is called Laplace demon. This is basically the essential idea of the atomistic modeling. So we want to describe everything at the fundamental level, these atoms, the motions. And from that motion, we want to predict the properties and also the process of the materials. So this is the essential idea. All right, so let me first contrast two types of the material modeling, continuum versus atomistic description, with the example of the dopant diffusion in silicon. So in silicon, when you want to dope the semiconductor, then you flow. One of the methods is to flow the gas of the dopant atoms, and then these dopant atoms diffuse into the semiconductor, and it can form and it can generate the carriers, right? And so here, here we want to describe the diffusion of these dopant atoms. So in a continuum description, we first coarse grain these atoms. So each of the dopant atoms are distinct object, right? So there's atoms and the silicon. All right, but in a continuum description, we want to average out, okay, on a certain position of in a spatial position, we average the concentration of the dopant and assign a function, continuous function. Although in reality it is not continuous, but we can approximate it as continuous function, the concentration as a function of the depth. All right, and then from the first row of the fix, it detects that the flux, the dopant flux, is proportional to the minus of the gradient of the concentration. So the dopant atom flows from the high concentration to the low concentration. It gives you some dopant flow. And then in combination with the continuity equation, you arrive at the fixed second law, which gives you partial differential equations about the concentration, right? And in the case of the single step diffusion, we have an analytic solution that is made of the error function. And as a function of the time, we have this changing in the concentration. Right, so this is basically the continuum description. It's very powerful and it's described very well the diffusion of the inside the material. But what is the limit of this fixed law? The first, at the atomic scale, at the nanometer scale, where the individuality of the dopant becomes significant. So in this case, the coarse grain approximation does not work anymore. You have to describe at the nanometer scale, you have the 10 angstrom or the 100 angstrom, so you can see the atoms. So the more precise description of the dopant diffusion, you have to introduce individuality of the dopant. The second, so in the fixed law, it is assumed that this concentration is not so high that the dopant atoms does not interact with each other, right? So it is somehow they do not interact. But when the density of dopant is very high, then you have to consider dopant interaction. In this case, the fixed law does not within the fixed law you cannot introduce such a term. And lastly, even though the usual materials, the diffusion coefficient is purely empirical. So, Berkeley material, it is well known. But however, if you are interested in the diffusion along the interface or the grain boundaries, or sometimes you want to study new materials, then every time you study the new materials, then you have to measure the diffusion coefficient, which is not so easy job, right? So, in this case, this is the empirical, the parameter is also the limit of the fixed law. So such a problem can be addressed by the more fundamental description using the atomistic view. And so atomically, there are three the mechanisms for the atomic diffusion. The vacancy mechanism, the most well-known, and in this case, the dopant atoms are interchanging sites with the vacancy, and this vacancy is moving around, which effectively gives you an idea. It gives you the diffusion of the atoms. And also the interstitial atom, it directly diffuses through the material. And also in the interstitial C mechanism, in this case, this interstitial atom pushes the atoms at the atomic lattice site, and this kicks out, and this lattice atom becomes interstitial, and such a process, the process is continuous, and it results in the diffusion of atoms. So which one is the dominant? It depends on the dopant species. And in the case of the boron, the dopant in the silicon, more detailed view is as follows. You have the silicon atom, you have the vacancy, then the silicon occupies the vacancy, and there is a vacancy, then leaving behind the vacancy, and this silicon is jumping into the vacancy, and now the boron can jump into this vacancy, right? And so the vacancies are moving around, and effectively you have the diffusion of the boron. It's quite complicated, right? So therefore, if we know, so this is the atomistic mechanism, and it is well known, and therefore, if we have the accurate interaction between the atoms, then we can actually describe the dopant, the diffusion of the dopants, the most fundamental, the basis. And also this the atomistic decreases the interstitial atoms, so we can go further to look into the mechanism. And this is the interstitial atom. And in order for this interstitial atom to jump to the next site, it first break the bonds with the lattice atom, and also the pushes out the neighboring atoms. And therefore, the energy increases along the path, and the maximum energy state, which is called the transition state, the energy difference between this transition state and this original site is called the activation energy. And therefore, you need enough the energy to overcome the barrier, which comes from the broken bond and the strike repulsion. Right. So within this statistical thermodynamics, within the harmonic transition state theory, the rate of the jump. So how many jumps you can jump from one side to the other, it depends on the product of the two parameters. The first one is how many times you attempt to cross the barrier, which is called attempt frequency, which is typically similar to the phonon frequency. And another the quantity is the probability that, because in order to overcome the barrier, you need a kinetic energy that is higher than this activation energy. And from the statistical mechanics, you can find that this probability is actually given by the Boltzmann factor of the activation energy. So this rate of the jump is called Arrhenius rate equation, and it gives you once you know the activation, the barrier, then it gives you how many times it jumps from one side to the other, right? And given this jumping rate, now we can actually obtain the diffusion coefficient of the dopant. So so this is the basic random walk problem, and it makes the jumps randomly. In this simple 2D example, there are 4 directions you can jump: 0, 90, 120, and 270 degrees. And if we trace the x coordinate, and this is theta. Theta 1 is the angle it makes at the first jump, and theta 2 is the second jump, and etc. And so the x position is a combination of the a times cosine the thetas. Okay, the sum of this quantity. And if you take the average of this x quantity, then since these 4 angles can be is a random number, so it has equal probability. And if average it, then the cosine average is simply the 0, right? So the position is 0. However, it does not mean that it always comes back to the original position. Some of the particles, this is the statistics. So some of the particles are on the right side and some particles on the left side. Okay. So therefore, so we want to know how far it went from the original position. In order for that, we have to calculate the x squared instead of the x, right? And then if we take the average, then now we have some of the finite quantity, half of the n times a square. Okay. Similarly, we have the distance along the y direction, y square. The expectation value of the y square is half of the na square. And so the total, the square distance from the original position is given by n times a square. And if the t is the diffusion time, how long it passed from this original position, then it t times theta. Theta is rate of the jump that we have discussed just before, right? And then it gives you how many times it jumped for a given time t. Okay, so n is equal to theta t, and so this is the L square expectation value. The L square is a square theta t, and this is the prefactor is equal to 2 times the d, and d is the so-called d is well known the diffusion coefficient. Therefore, the diffusion coefficient is given by was related to from this Arrhenius rate equation. It is related to the activation energy, right? So here I want to show you that once we know the detailed interaction among the atoms, and then one of the ways that we obtain the diffusion coefficient is to calculate this activation energy, and it connects the microscopic quantity activation energy to the macroscopic quantity diffusion coefficient, which is observable, right? And therefore, this from the sum of the theory, you can connect from the microscopic or atomistic information to the macroscopic quantity, right? This is one of the example. All right, so then here the key point is how can we obtain this the interaction among the atoms? Such an interaction among the particle is called interatomic potential, or we call it classical force field. So let's discuss the most simple example, H2 molecule. So you have this H2 molecule, 2 proton, and then this x-axis is the proton and proton separation, and the y-axis is the energy of this, the system or the hydrogen molecule. You can say that this is experimentally verified, or you can say that this can be computed, computationally using the quantum mechanics that I will discuss later. Okay, so anyway, this is a reference to interaction. Okay, so which we actually do not know much before we actually measure or calculate quantum mechanically. But the good thing is that you do not need to know the whole the potential curve, because at the usual condition, a typical condition, at the room temperature or even maybe several hundred of the Kelvin, the atom vibrates. So the minimum energy point gives you an equilibrium distance, the proton-proton distance in the H2 molecule, and the vibration distance is actually less than 100 angstrom. It's a very small vibration. If you see this vibration, you don't actually recognize that it is actually vibrating. It's very small vibration. Therefore, in such case, we can actually expand the whole interaction curve or potential curve around this the equilibrium distance. So this is this Taylor expansion. This x0 is the equilibrium distance, and we have the first this constant, and this is first order. But since it's at the minimum, so the first derivative is vanishes, and so you are left with the second derivative, and this is nothing but the Hooke's law, right? It's harmonic or the spring model, and therefore that means near around the equilibrium distance, you can approximate with very good precision. You can approximate this whole interaction curve with the simple the harmonic potential of the spring model. Therefore, you can visualize that this H2 molecule is actually connected by a simple spring that follows the Hooke's law. And from the experiment or maybe the computation, it is known that this effective spring constant of H2 molecule is 573 Newton per meter, which means that if you have the H2 molecule and if you can expand, the following the Hooke's law, in the all the way, all the length, which is not the case, then maybe this is 573 Newton is around the weight of your usual, the grown people. And so, with your weight, the hydrogen molecule expands like 1 meter. Yeah. But remember that this is just one molecule, right? 0.1 molecule. So therefore, it is extremely the tight or the very, very strong the spring, right? And so that's why, the vibration is very small. Okay. So with this, the effective spring, the constant, then you have the interaction between this H2 proton-proton. And so you can describe the motion of this H2 molecule or the vibration. So since this, let's consider this, just the symmetric, the vibration. Then if you are just hide one part of this molecule, then this is the same as the spring or the mass attached to the wall with the spring. And in this case, the spring constant is actually the 2 times the original, the spring constant, because, if you stretch the spring to here, then your mirror image or the other side of the proton is also expands by delta x, and therefore overall it expanded by 2 delta x. And so the effective spring constant is actually the 2 times of the this original, the spring constant. Okay, so this is simply the problem of the mass attached to the spring, which we a solution we well know from the general physics. And here our question is that from the initial condition of the x0 and v0, or the position and the velocity, what are the position and the velocity at the later time t? Okay, so this is the most simplified simplified vision of the what the Laplace has mentioned in his Laplace demon. And so this is the what we want to do. And in order to obtain these two quantities, we solve the Newton's equation of the motion. The first one is F equals ma as minus Hooke's law, and this is the second derivative of the acceleration, second derivative of the position, and the first derivative of the velocity, and also the velocity is derivative of the position. And therefore, you have a set of simultaneous differential equation. Okay, and we know that each solution can be solved or obtained by analytically, and this is x and v, and with the initial conditions, it is harmonic vibration with angular frequency and also with the period. Okay, so this is simple and we can obtain analytically. However, this is only limited to the simple harmonic oscillator. If there are many particles or the interaction becomes complicated, you cannot obtain such an analytic solution. And therefore, we have to solve it numerically. Okay, so how can we solve that? It's the same equation numerically. So the first step is to discretize the time. Time is originally the continuous variable. However, the computation in a computer cannot deal with the continuous variable. So you have to discretize the time. Okay, so 0, delta t, and 2 delta t. So delta t is the time interval. And then our question becomes given the position and the velocity at the time t, what is the next the position and velocity at the next step? Okay, here we also make use of the Taylor expansion. Okay, as x t plus delta t is given by this Taylor expansion, and this first derivative is the velocity. The second derivative is the force, right? F equals ma, or a f over m, sorry. And we ignore the last of the term, which is the truncation error. And also, so this is the Taylor expansion in the position, and then this is the Taylor expansion in the velocity. The velocity, we have the first derivative, which is corresponds to the force. And the second derivative, we do not have such a good estimate, so we can simply ignore the second derivative. And so, in the case of the velocity, we have the larger one order larger truncation error. Okay. Anyway, we have the form that we can. So, given the xt and vt, by plug them into this equation, we can obtain x t plus delta t and v t plus delta t. Okay. So in this way, you can proceed in time. Okay. Right. So let's take the concrete example with this, the mass and spring constant and the position at the 10 centimeter and the V0 equals to 0. So to simply stretch the spring and then let it go. And in this case, the period is 1 second. So here, these are the numerical results in comparison with the analytic solution and with the different time step. In the first case, we take the very small time step, 10 to the minus 4 seconds. Okay, then we have an almost identical solution to the analytical one. Okay, so position and the velocity, harmonic vibration. Now you increase the delta t by 10 folds and use the 10 to the minus 3 seconds. Then initially it looks reasonable, then the error becomes larger. Okay, then you increase further by 10-fold, 10 to the minus 2 seconds. In this case, well, after 2 or 3 vibration, then error is noticeably the larger, and it becomes larger and larger. Okay, so from here we can see that, you know, in order to obtain the accurate numerical result, there is a certain amount of the time step. The delta t should be small enough. So, however, you should not indefinitely use the indefinitely small time step, because if the time step is too small, then in order to proceed in a certain given amount of time, we have to calculate, you know, much more computation. For example, if your delta t is 10 to the minus 6 seconds, then just 1 second simulation, you have to go 1 billion time step, which is a huge computation, right? So there should be a certain, you know, amount of the trade-off between the small time step with high accuracy and the large time step with the high speed. Okay, so in this case, the 10 to the minus 4 was the thing that we have to use, but this is too small, and so actually the large error that comes from the velocity, because in the case of the velocity, the truncation error was 1 order higher than the position. Therefore, we needed to do something more in this velocity. And then, we have expand one more term with the second derivative of the velocity, which corresponds to the derivative of the force. But we do not have but for the derivative of the force, we use finite difference. Okay, a prime delta t is equal to actually f t plus delta t minus ft over delta t. Okay, but the caveat is that this is the first is the next step. We have the information at the t, and we want to predict the t plus delta t. But what we need is actually the information in the next step. Okay, but here this one we can overcome because we can first predict the position. Okay, then the velocity. Then we can, using this the current position, velocity, and also the force. The force comes from the position, and using this expression, we can estimate the position in the next step. And using the position in the next step, this prediction, we can calculate the force, because F equal minus kx, and so next position gives you an estimate of the next force. And using this force, we can now obtain this difference. And then we have the second derivative of the velocity, which reduce the truncation error in the velocity. So this is the most famous so-called the velocity bullet the method, and this is a sort of the predictor correct method. So using this velocity bullet, the algorithm, then with the same time the step delta t 0.01 second, which was gives a huge error in the naive the method, was in this case is almost identical to the analytic solution. You can further increase the time step, right? 0.05 second, you still have the quite good. 0.1 second, it looks reasonable, right? So although there is some of the difference, but you can see that actually the error overall, the magnitude does not increase. In the case of the naive method, no, this energy was actually diverging. However, in this case, the energy is the constant, but the period or the oscillation of the frequency is slightly higher in this the velocity volume. All right, so this is quite good, the method. And so, but what we can learn from this example is that in order to describe one vibration or the reasonable the vibration, then if the one vibration is consists of the 1 second, then you need at least or in a 10 or 20 the time steps within that time interval or the one period. Okay, in the case of the molecule or the atomic system, the typical the vibration frequencies tend to be 13 to 14 hertz, right? So it vibrates this amount of the times within 1 second. Therefore, the vibration period is around 10 to 100 femtosecond. Therefore, the time step to describe the molecular the dynamics is at least should be around 1 femtosecond, which is extremely short time step, 10 to the minus 15 seconds, which is is quite the limit the simulation, right? So anyway, so this is the aggregate time step is at 1 femtosecond in the molecular simulation. Okay, in reality, in actual materials, there are many the atoms, and we can say that they are connected by the effective spring. And if this is just a spring that we have discussed before, then this is the two-body or the pair potential, which is in each sum will give you the total potential energy. But this is not the only the potential type, because if the spring are connected, in the form like this, then it effectively has a three-body potential. Okay, or in general, all the atoms are positions are needed in described potential. So there are many different types of the potential, and in order to get the force, we take the derivative or the gradient of the potential. It gives you the force that a certain atoms feel at a certain moment. Okay, and using that force, we can simulate material evolution. Okay, so the problem is that how can we find the proper form or the parameterize the potential? First, it depends on the bonding type. In the case of the ionic bonding, you certainly need to include the Coulomb potential. In the covalent bonding, you need the three-body term, and the metallic bonding. Okay, so depending on the bonding types, you have the proper forms that reflect the underlying the quantum mechanical bonding nature. Or most generally, there are relative force fields, which consist of the huge numbers of the very different number of the terms that describe various kinds of the interaction. Okay, so there are mathematical form, and the parameters in this the formula, they are fed to a initial result or quantum mechanical result or experimental data. Okay, but the problem is that the classical potentials are developed only for a small number of the molecules. The mostly unary system, just one component system. Because developing such a functional form and also the parameters are is highly non-trivial. Okay, and also furthermore, in many materials, bonding types are actually rather mixed. Not purely ionic bonding, but half ionic, and half covalent. And or sometimes there are ionic, covalent, metallic, but all the bonding types are all mixed into one single materials. Okay, so in that case, it is difficult to choose a proper the function type. And also the selection of the function types and also the parameterize them, it actually depends on the human intuition. And over the world, there are not many people who can actually develop such the force field. Okay, it is quite powerful, but it's very limited in material in dealing with the diverse materials. If you have the classical potential, then in the size and the time scale, this classical potential can describe up to some maybe 100 atoms, number of atoms, maybe 1 million atoms, which correspond to around the 100 nanometer length scale in 3 dimensions. And also in the MD simulation, because our time step is 1 femtosecond, it is maybe the maximum time that you can simulate is around the 10 nanosecond or maybe 100 nanosecond. Okay, far less than the microsecond. Okay, so this is quite limited. Okay, in contrast to in the case of the continuum or the finite element method, you can simulate in any kind of the time scale. The length scale is maybe around its accuracy stops at the nanometer scale, but over the macroscopic scale is no problem. Okay, so the classical potential is quite limited in size and the time scale. However, many equilibrium properties of the solid and liquids can be obtained, and also the sum of the process can be directly simulated by the molecular dynamics. Okay, then in the following slides, I will show you the examples of the classical the simulation. But before I show you some of the examples, let me discuss about the simulation condition. There are several different kinds of the simulation condition. If the fixed number of atoms and also the fixed volume, and then if the system is isolated from the environment, there's no exchange of the matter or the energy, then this is called MVE ensemble or MVE ensemble simulation, or we call microcanonical ensemble or adiabatic simulation. So this is the basically isolated system. The system may be up in the space. Okay, but if you fix the number of the number and the volume, but if the system is in contact with the thermal base temperature T, which exchange the energy, then it is called MVT or canonical ensemble. And you can also allow the volume can expand or the shrink according to the external pressure. And in this case, it is called NPT ensemble. And these two are called closed system, meaning that it can exchange energy and also the pressure or the mechanical energy in the form of the pressure, but it does not exchange the matter with the environment. The most general the simulation is in this case you can change the number of the atoms, and in this case this is called the grand canonical ensemble. This is the open system. Okay, so the popular simulation type is MVT or the canonical ensemble. In this case, we control the temperature using some hypothetical thermostat, because in reality you have the thermal bath, which has the huge number, the macroscopic number of atoms, but here we have at most several tens of thousands or up to the billion atoms. So it is not that enough to simulate the thermal bath, and therefore we have to introduce some of the artificial or external thermostat which control the temperature. And there are many different types. The most the popular is the NOSE developed by the NOSE and Huber. And here you have some of the fictitious parameter S, which interact within the Hamiltonian. It interacts with the atoms. It is not seen in the simulation, but it is hypothetically interact with each atom, and it kicking is like resembles some of the motion. Then if you have the atoms on some of the surface, then from the thermal base there's some of the kicking from the thermal base, and those Huber thermostat simulate that kind of the kicking motion. So I will show you some of the example of the MVE and the MVT, the ensemble simulation with the example of the water molecule. So the left is the MVE ensemble, and you can see the periodic and the regular vibration of the water molecule. So this is the energy is conserved, so it is a closed system. In the case of the MVT, however, you can see that sometimes it vibrates widely, and sometimes it vibrates with a much smaller amplitude, right? Its motion is somewhat chaotic, and overall, on average, the vibration energy is correspond to the given temperature. But this is one example of the MVT ensemble with the fictitious thermostat. Okay, So then I will show you some of the example of the classical MD simulation. This is a silicon carbide. We also have a thermostat and carried out at 600 Kelvin. So this is a system that we have that we are simulating, but this is not the isolated one. We applied purity boundary condition, and therefore the simulation box is repeated in every direction. Okay, in a three-dimensional in every direction, and therefore it is essentially infinite system with purity boundary condition. And we have used the LAMPS package for the MD simulation. And so this is a 600 Kelvin. You can see a small vibration. Okay, that's it. Okay, so from the simulation, you have the trajectory of the atoms. And by analyzing trajectory, you can obtain the temperature or the velocity. Thermodynamically, the temperature is related to or nothing but the mean kinetic energy, right? So from the trajectory, we calculate the mean kinetic energy and divide it with the 1.5 the Boltzmann constant, and it gives you the temperature of the system, right? Is on average is 600 Kelvin, and therefore it is what we have imposed in the beginning, 600 Kelvin. So meaning that the thermostat is actually working, right? There are some small fluctuation. This is because we are dealing with a finite system. As you increase the size of your simulation box from the 5 by 5 up to the 10, 10, 10, or even further than, we have a smaller and smaller fluctuation. Okay, so the fluctuation is the characteristic of the finite system. And also, you can calculate the distribution of the velocity by looking at the velocity of the individual atoms. You have this distribution, and initially in the beginning, this is what we have started. Okay, this is the initial velocity distribution, but within less than 100th femtosecond, it quickly equilibrates, or its distribution becomes converge into a certain form, and that is nothing but the Maxwell-Boltzmann distribution, which is the given by the statistical mechanics. All right. So the simulation, it is obvious, but the simulation follows these statistical mechanics. Okay. And then we can calculate the heat capacity. Heat capacity is the definition is the temperature derivative of the internal energy. And here, internal energy means kinetic energy plus the potential energy of the whole system. So you can do this. You can calculate this because you know the position and the velocity. You can calculate everything you need to compute that. All right. So this is the temperature of the simulation. This is the energy of the silicon carbide, and right, this X is the simulation result, and you can see that it is almost linear with respect to temperature, and its slope is this number. And if you convert this into the joule per mole per Kelvin, then this is 50. All right. And in fact, this is nothing but the Dulong-Petit law, which states that from the equipartition theorem, any classical system has the heat capacity of the per atom at 3R. Okay, is number of the degree of freedom, and so 3R times and the 2, and so this is the 50, almost the same number. All right. So yeah, this is because we are treating these atoms classically, and therefore its heat capacity is nothing but Dulong-Petit's law. In reality, you know that experimentally this is not a constant. So such an the Dulong-Petit law follows only at the high temperature, and at the low temperature it is much more suppressed because of the quantum effect, and it finally becomes a zero at a low temperature. And it is very well fitted to divide model. We can do this, but in order to obtain such a heat capacity within the quantum mechanics, then rather than MD simulation, we have to calculate the phonon spectrum and apply the quasi-harmonic approximation. So in that way, we can obtain very precisely such an experimental the data. Okay. All right. And this is the carbon in alpha ion, the diffusion of the carbon. And this black one is the ion, and there are some of the carbon atoms in an interstitial site. And here we are simulating the diffusion at 1300 Kelvin. So in a previous the model, well, we have discussed about the activated state, but in this case, the diffusion occurs very fast, and so we can directly calculate the mean displacement out of the MD simulation, right? And so you can see these interstitial carbons are, moving. Carbon atoms are moving around, and from that trajectory, we can calculate the mean square displacement, and it's with almost linear slope. And this slope gives you a diffusion coefficient, which is the 1.4 times 10 to the minus 10 meters square per second. And by changing the temperature, 900, 1100 Kelvin, then we obtain another data. And then with the plot, this is log D, log of diffusion coefficient, and versus one of the temperature. And here, this is a simulation data. And this blue one is the experimental measurement. I got this from this reference here. And you can see that it's quite close. And also, is the slope of this diffusion coefficient gives you an activation energy. And from the simulation, it is around 1 electron volt, which is quite comparable to experimental value of the 0.83 electron volt. So right, so you can directly simulate such a diffusion process, because in this case, this is high temperature simulation, and therefore you can directly observe such a diffusion within your computation time. All right, so this is the example of the Melty-Kenchi or the amorphous simulation. In this, maybe you have seen this kind of the making the glassware, where you melt the glass, and then as it cools down, you can make any kind of the shape. Because of this amorphous structure has a very high structural flexibility. So we can simulate such a Melty-Kenchi process within the simulation. Yeah, much less interesting anyway. Right. So in the high temperature liquid state, atoms are moving around, but as it cools down and as it passes through the glass transition temperature, then it solidifies and into the amorphous structure. And finally, we can obtain the amorphous structure. The one caveat of this Melty-Kenchi simulation is that in reality, such an amorphization or the cool down process occurs maybe some second or some minute time scale, but we cannot simulate such a long time scale. Therefore, we very highly unrealistically high quenching speed. Then with only that speed that we can simulate such a process. Okay. And we can also obtain the melting temperature of the various material from the simulation. So this is the example of the calcium oxide. But in fact, this is the potential. This is not the classical potential, but this is the machine learned potential that I will discuss in the last part. But anyway, to give the potential, then this calcium oxide, this can be the solid or the liquid, they are shown with the color, the both atoms. But if it is in a solid, then it is the green, and if it is the blue, then it means this is a liquid. And within the simulation box, you can make the interface between the solid and the liquid. Okay, and if at a given temperature, if the free energy of the solid is lower than liquid, then the solid region will take up the liquid part because it is condensed at the solid state phase. So this is what happens actually in the 1350 Kelvin. You can see that right. So we start with the solid liquid interface, but eventually we end up with the solid phase. The meaning that at this temperature, the free energy of the solid is lower than the liquid. Then you increase the temperature by 100 Kelvin on the right scale, on the right figure. Then now the liquid wins, the meaning that at this temperature, the free energy of the liquid is lower than the solid. Okay, and then we decrease by 50 Kelvin, and now simulated at 3100 Kelvin. Now, so in the beginning, there's some of the tug of war, right? And then, but eventually the liquid wins. The meaning that still at this is the above the melting point. Therefore, from this simulation, we can narrow down the melting point within 3050 to the 3100 Kelvin. And actually, this is the within the experimental, and experimentally there are two the experiment, and they are within this range, and therefore this is within the experimental error. Okay. Okay. So this is what we can do with the classical potential. But more directly, we can also actually obtain the free energy directly from the simulation using some sophisticated method called the thermodynamic integration and semi-grand ensemble method. This is what we obtained from the potential, the MgO and the calcium oxide eutectic phase diagram. This is one of the most archetypal eutectic phase diagram. And the various symbols indicate the phase lines that were identified by the experiment. Okay, and this is a melting point, and this is a liquidus line, and a solidus line, and a sorbus line. Now the simulation, by directly calculate the free energy, you can obtain, all this phase boundary. And there are two, but let's ignore this PB. Let's focus on the scan NMP here. Then this orange line is closely reproduce all the phase, the boundary that was measured experiment. This is amazing, right? This is pure computation without any the knowledge from the experiment, but still you can obtain the same phase diagram without that much experimental effort. Okay, and also this is another demonstration. This is still we are using the machine learned potential. This is crystallization of the germanium telluride. This is the famous phase change material. It very rapidly changes the phase from the amorphous to crystal. And here, this is simulation of the crystallization process. And there are empty parts. This is not really empty, but they represent the amorphous region. And as the simulation evolves, then we can find the crystal region grow here and there, multiple nuclei, and eventually they are rock sort structure, as you can see. And eventually we have the polycrystal, right? Looks very realistic, right? So we can do this. And this is the interface reaction between the nickel and the silicon. This is one of the very famous semiconductor process, the crystallization. And we can see that nickel and silicon interact and make the compound, make the alloy within the region, interface region. Right. Okay. So you can do this. All right. Let's change the gear and talk about this ab initio method. Okay. So classical potential is good, but the problem was that there are very small number of the potentials are developed. On the other hand, we can approach the same problem, more fundamentally using the Schrödinger equation, one of the most fundamental equation in nature, by treating the electrons and the nuclei, all of them quantum mechanically. I will not go into the details of this equation, but this is very, very highly complicated. You cannot solve this, even for a very small number of the electron nuclei. So there's no way that we can solve the whole the equation for the real material. But there are two approximations actually enable us to calculate or apply this quantum mechanics to our materials. The first one is the Born-Oppenheimer approximation, or also known as adiabatic approximation. So here we separate the nucleus and electrons. The nucleus is much more heavier than electrons. Therefore, to the electrons, nucleus is moving too slowly. It's like almost like frozen there, and therefore we only needed to treat the electrons quantum mechanically, and for the given position of the atoms, and then from that the result of the energy, we can treat the atoms or the nuclei or the ion classically that behaves with the potential that is given by the energy that we have obtained from the quantum mechanics applied on the electrons. All right. So therefore, basically we are separating the nucleus and the electrons, and the electrons we solve quantum mechanically, nucleus the classically. So that's what is the major idea of the Born-Oppenheimer approximation. But still, we have to solve the electrons in many-body electron the system, which is quite complicated. There are huge number of the variables. Let's take the example of the C60. C60, you have some of the hundred of the electrons, and all of them has three dimension, moving in three dimensional. Therefore, your wave function has the dimension of the several hundred or even 1,000, which is completely unsolvable using any kind of the supercomputers. So then, Kwon and Sham developed the density functional theory back in very long time ago, and the Kwon received the Nobel Prize for developing that theory. And according to this theory, this many-body Schrödinger equation is converted into the single particle Kwon-Sham equation, right? It's much simpler than the original equation. Now this is solvable. But the problem is that all these complications all of them are condensed into this exchange correlation function, and whose exact form is not known. Therefore, we have to introduce some approximation in this exchange correlation potential, and there are some of the theory, LDA or local density approximation or generalized gradient approximation. And now today, this GGA is quite favored approach, and over a wide range of the materials, it gives a very the good result. So the advantages of the density functional theory is that there are no empirical parameters. Even though there are still the parameters included in this approximation, but it does not change with the material. It is fixed in the original development, and once it developed, we do not change the parameters, and we apply to any kind of the materials, and even for the materials that we have not synthesized there's no experimental information. So this is why this method is called the ab initio, or the first principles. And the second, even though it is there are no empirical parameters, it's highly accurate, and it is also reliable. Reliable means that it is not 100% accurate, but it has some error, but the error is systematic. It's quite uniform the error. So we know, for example, if the lattice parameter is overestimated, it is overestimated throughout any kind of the material. It's a systematic error. This is very, very popular approach. And so one example in the Bas-Briena emission package, one of the most popular program, and this original paper was cited, tens of thousands times. And also at this moment over the world, the supercomputer centers, around half of the supercomputers, they are learning one single program, the VASP. It's a very popular program. But this is commercial packaging, and the Quantum Express is the more open software. Okay, so using that the density functional theory, we can obtain various properties of the material from ab initio without any empirical information. For instance, this is the kappa, and by changing the volume, we obtain the minimum of the volume and or the lattice parameter, and also its derivative gives you some of the elastic constant. And from the theory, and this is the experiment, they are really very well, and so it's very accurate. And so this is a phonon spectrum of the gallium arsenide. So in order to measure the phonon spectrum, we have to first grow, quite maybe millimeter size of the single crystal, and you go to the neutron scattering center. There are not many places in the world where they have the neutron facilities, and then you measure the phonon spectrum, and that's what you get in this here, the diamond, the symbol, this experiment. But at the same time, you can download the program, Quantum Espresso, just install it with your computer, and maybe half of the day, it will give you the phonon spectrum of this line, which is almost indistinguishable from the experiment. So highly precise. And also you can calculate the thermal conductivity. So phonon is basically the second derivative of the energy, and the phonon thermal conductivity is related to the third derivative. And there still we have some of the packages to calculate the thermal conductivity, and for a wide range of the materials. And you can see that this is the wide range of the data, the value, and agree very well, right? So these first principles and experimental data. And also the band structure. So tensor functional theory, one thing that is clearly different from the classical the dynamics is that it gives you the energy spectrum of the electron, which is the band structure. And this is the kappa, and this is gallium arsenide, and these are the data that are obtained from the RPS, the measurement, and which is compared with the computation, which works quite well, right? So it gives you a very reliable electron structure. How about the band gap? In the case of the band gap, actually the PBE approximation that the GGA that we had mentioned before, it gives you a systematic error, and it gives you maybe for most of the material, the band gap is underestimated by 30 to 40%. But then we know why. We know why there's such a large error, and so we develop another level of the theory, which is called the GW calculation. And this is what you get from the GW calculation. Of course, this is much more expensive. In the case of the GGA, to obtain the band gap is like $1 US dollar. But if you apply the GW calculation, well, maybe more than $100. It's much more expensive calculation. But if you need it, then you can apply it, right? And you can obtain very accurate the band gap. And also the effectiveness, which reflects the curvature of the band structure, which this is silicon, and also very well with the experiment. Okay, so first principle calculation is very accurate. The only problem is it's much more expensive than other classical potential, of course. And it further limits its computation scale. Like 1 nanometer calculation is quite a big job. And also about time scale, going beyond the nanoscale, well, it will take several months of the simulation time. So it's very expensive computation. But still, if you can, then it will give you a very highly accurate and reliable result for any kind of the materials. Then we arrive at the last topic, the machine learned potential. Okay, so the classical potential, fast, good, but there are not many materials are developed for potentials are developed. In the case of the quantum mechanics, you do not care about the material, so it's okay, good, but it's too slow. So machine learned potential actually combine the advantage of this two approach, right? And it tries to achieve the accuracy of the DFT, but it also achieves the speed of the classical potential, right? That is possible by making use of the machine learning technique. It was originally developed by the Bella and Parinello long time ago. Actually, if you track the citation of this paper, then in the beginning, it did not receive much attention, but maybe around the time of the AlphaGo, now the citation increases exponentially. This reflects how popular is this method now. Okay, so the basic idea is the machine learning. We provide the DFT data, at a small scale, but highly accurate the energy and also atomic force data. And the computation machine learns, like a neural network learns the information. And then for the larger system, it predicts the energy of the another system, not solving the Shukonshan equation, but by inference from the machine learning model. Okay, there are actually two ingredients in this machine learning method. The first one is that we decompose the total energy into atomic energy. The wave functions are dispersed all around your system, and therefore you cannot, slice the energy like you cannot slice the electrons. However, they assume that total energy is the sum of the atomic energy. Actually, we have shown that actually this atomic energy, although it is not unique, can be defined at the DFT level. So there is some theoretical, the support that such a decomposition is valid. And the second ingredient is that using the machine learning or neural network model, the input feature here, so this atomic energy depends on the local environment. So how these atoms are configured around certain atom. And here they have encoded such a local environment into a set of the function, so-called symmetric function, which guarantees the invariance on the rotation, translation, or the permutation. Okay, so this basically reflect distance distribution and also angle distribution around a certain atom. Or recently there is another descriptor called the convolutional graph, which we think is quite powerful, but this is the much more expensive or more complicated than the symmetric function. Okay, so I think that they are very smart in proposing such a symmetric function and using them as an input feature of this atomic energy. Anyway, it works. It works very, very successfully in many examples. Not everything is perfect, but here the caveat is that this machine learning potential is actually data-driven DFT calculation. Therefore, data is everything. The success of the potential, or the accuracy of the potential depends on whether we can find a training set, right? So suppose in a local environment space, if this is the target simulation, then our training set should include, okay, so right just outside of target simulation, because this is the huge space, and therefore you do not need to, or we should not sample the whole space. But somehow we can, if we can sample the simulation tightly, then you are very successful, right? So this is the one of the key points in developing the machine learning potential. But this one, you do not need the huge expertise like in developing the classical potential, but just maybe you're the physical or the chemical intuition in your material system, then it is enough to make the training set. All right. So if we compare the speed of the machine learning potential, then this is the example of the silicon, and this is the number of atoms that you can deal with, you are dealing with, and this is time that required to calculate this the energy. And the DFT calculation is scaled with the order of the entity cube. So it is very rapidly the computational cost increases. But in the case of the neural net potential and also the classical potential, it increases with the order n, okay, because of the locality. And so this is an increase is very much more slowly with respect to the number of atoms. And therefore, the machine learning potential allows for the simulation of the TFT accuracy up to the 100,000 and up to 10 feature scale over the time scale of the nanosecond. Okay, so this is slightly smaller than classical potential, but the good thing is that you can develop potential. You can develop potential for any kind of the materials. That's a good thing. Right. So, and in our group, we have developed our own package called the simple NN for the training and also the executing. Executing is and the simulation is made with the lamps, but we provide interface between our package to the lamps, and we are having been developing some of the fundamental methodology and also the various diverse applications. Some of the applications that I have shown actually made use of the machine learning potential. Okay, and for the last amount of time, then I will show you the example, the crystal structure prediction. Okay, so this is motivated by this observation that in the case of the element or the one component of the system or the binary system, we have almost every compounds are known, inorganic compounds are known. But in the case of the ternary or quaternary, we still, there are not many the regions, domains have been explored experimentally. So therefore, it will be very very helpful if we can find the crystals with the unknown domain theoretically before we experiment. And then if we can find this useful property, then we propose to the experimentalist about the synthesis of the certain materials. So that is one of the dream of the theoreticians. And in order to predict the crystal structure, we need to obtain, we try various kinds of the crystal structure and find the global minimum. And that the global minimum in the free energy space that corresponds to the equilibrium structure. All right. So this is nothing but, searching through the energy space, energy landscape. The problem is that the number of the configuration that you explore in the configuration space is huge, is astronomically huge. And for very typical system, the number of the possible configurations are usually 10 to the 15, 21, 23. It's just meaninglessly the huge number. Therefore, you cannot try every possible configuration and compare the energy, right? So instead of such a brute force comparison, people have been making use of the heuristic approach, such as a genetic algorithm, the hereditary or the permutation or the mutation or the random generation. And so, and they combine this, they have been combined this with the density functional theory. One of the most famous package of this structure prediction is called USPEX. And that they have been very successfully have been exploring the new materials like the superconductor on the high pressure or the energy materials. But you can see that they are mostly just limited to the binary system, very rarely ternary system. And therefore, this is because of the speed of the density functional theory, because it's too slow, you cannot deal with such a complicated system. Therefore, it would be useful if we can replace the density functional theory with the machine learning potential. Then it will enable us to calculate or the explore the crystal structure prediction for the more complicated system. But the problem is that we do not know the crystal structure. That's why we are trying to find the structure, right? If we do not know the crystal structure, then it is very difficult to train your potential. You have to provide the training data to for the machine learning method to learn the data. Okay, but you do not know the crystal structure, then we have the blank-handed. So in that, we have proposed some years ago about making use of the multi-cancer. Oh, I will show you the next slide here. It will be better. So the multi-cancer simulation. So instead of the crystal structure, we have applied the melt, the liquid, and cool down. Then you obtain the amorphous structure. These are the disordered structures. However, it's local order. The configuration around certain atom is actually resemble the configuration at the actual crystal structure. And therefore, by providing the data on this disordered structure, you may have a very good the model, the machine learning potential for delineating the energy of the possible configuration. That's what we have actually confirmed in the paper, that the machine learning potential with the trained over the disordered structures, they gave the energy difference in very close agreement with the density functional theory calculation. So they can be used in the structure prediction. And then we have developed the package of the predicting the structure using the machine learning potential. And I will not go into the details. And with that, this is spinner package, and we were able to deal with quite complicated ternary structure as well, with almost 80% success rate. This is a blind test, so we do not know the crystal structure in the beginning. The structure that end up with, they are agree with the experiment 80%. Okay. So what we can do is that we can try to find the new material. For example, in the case, this is the example of the ternary metal oxide. This is one of the most exhaustively explored compound. But there are still missing combination of the metal in this ternary metal oxide. And we've searched all these combinations, and we have found some of the combinations that can be synthesized with the negative Hall energy without phase separation. Okay, so this is one of the things that we can do with the this machine learning potential coupled with the structure prediction. Okay, so this is the final, almost final remark. So I have introduced, very briefly all the method in the atomistic the simulation, and I want to emphasize that actually, in particular, this the interest in the atomic simulation, in particularly in the industrial the domain, is increasing quite high. This is because there are two reasons, in my opinion. The first one is that cutting-edge extreme technology, like highly scaled semiconductors, they require quite accurate simulation and nanometer scale to increase the performance while lowering the cost. So therefore, this is called the digital twin. So without the experiment, you can do the same thing with the computation. The problem is the empirical approach based on the experimental informations are limited. So therefore, the continuum simulations is quite popular in industry. There are many parameters that you do not know for such a very nanoscale domain. And therefore, in that case, this atomistic simulation is very powerful. And also at the same time, the human intuition. So experimentalists, they needed to understand what happens at the atomic scale for developing the more, maybe the solution to the problems, or develop high performance materials. But certainly the information, atomistic information, is very difficult to obtain experimentally, and also very rare. And so the atomic simulation, the process that we obtain from the simulation, can give the experimenters a huge intuition in their own application system. That's why I think this atomic simulation is very important in material science and engineering, particularly in the future. Okay, so that's the pretty much end of my talk. Thank you for your attention, and then I will take the question or the comments.
Well, thank you for Professor Seung-Han for the great lecture.